So in this video, we're going to talk about the stoichiometry of a reaction, and we're going to cover a few things here. We're going to talk about displacement reactions in this case, and in the course of the video, we're also going to talk about balancing equations and molecular structures, also how to write formulas for metal salts, as well as using the stoichiometric ratios. And the stoichiometric ratio is very important because we can use it to determine quantities based on one another. The overarching goal of the experiment is to actually use the stoichiometric ratio and a given amount of material to determine the amount of another material that's possible in a reaction. So let's jump right in. So what is a displacement reaction? Displacement reactions happen when you have metal ions or metal atoms in a particular compound or solution that get replaced by an atom of another metal. In this case, we're going to be replacing copper with iron. All right, so what's going to happen here? So I have here a solution of copper sulfate, and then add a known amount of iron filings. So iron filings are just really black powder. So I add a known amount of that, and then I'm going to heat this up, and then I'm going to look for the displacement of copper. You can see the change here. So that iron is actually going to displace the copper from the copper sulfate solution, and the copper, elemental copper, is going to precipitate out of solution. All right, so let's jump in. This is the actual reaction. So we're going to start with copper sulfate. We're going to treat that with iron 0, which is a solid, and then that's going to give me iron sulfate plus copper, right? And copper is a orangey metallic, shiny metallic solid, right? So this is the reaction that we're doing, and this reaction is assuming that the iron 0, the solid here, gets converted into iron 2. We're going to talk about that in a minute. So here's the redox reaction, right? Because this particular displacement reaction is an example of a redox reaction. Redox is short for reduction and oxidation. And so one of your species is going to get reduced, the other one is going to get oxidized. So this is the net ionic equation for the top equation, right? So you have iron solid plus copper 2. On the other side of the arrow, you have iron 2 plus copper solid. And the iron solid and copper solid are both have an oxidation state of 0. So what actually happened is iron lost 2 electrons, right? You can see here, iron went to iron 2 plus, and then copper gained 2 electrons because it went from 2 plus to 0. And so you can also write that redox reaction as what we call a half reaction, which is shown here, right? Where you have iron going to iron 2 plus 2 electrons, and then copper 2 plus 2 electrons going to copper 0. So the iron gets oxidized and the copper got reduced. All right, so let's talk about this a little bit further. So this is copper sulfate. This is what it looks like. And we have copper 2 plus, and then the sulfate anion has a -2 charge. And the way that you write the formula for this is you just crisscross those charges. You take the 2 from copper and you you put it down where sulfur is, and then you take the other 2 from the sulfate anion and you put it down where the copper is. In this case, the 2's are going to reduce, and you end up with CuSO4, where it's 1 atom of copper and then 1 polyatomic molecule of sulfate, the sulfate anion. So the 2's cancel out in this particular case. All right. So let's talk even further. So what happened in the reaction is I have iron 0 here, and that is going to react with a molecule of copper 2 or copper sulfate. Right, so let's look at what happens, and this is a rough depiction of this. It's not 100% accurate. It's the best I could do with PowerPoint. So iron 0 comes in, it hits the copper 2 or collides with the copper 2, and the copper falls out of solution, and then the iron 0 becomes iron 2 plus. So that's the redox part where the iron 0 gets oxidized up to iron 2 plus, and then copper 0 falls out of solution. So that's what we have down here. So this is what the iron 2 sulfate molecule looks like. All right, so that's a rough structure of what it would look like with iron and octahedral geometry. And so again, in this reaction, iron lost 2 electrons, so it got oxidized. Copper gained 2 electrons, so it got reduced. And so here's the copper over here that falls out of solution as copper 0. And again, this is called a displacement reaction. All right. And so here's another, here's the iron sulfate that gets formed, right? So we have Fe2 plus, SO4, sulfate, 2 minus. We crisscross the charges, and those 2s are going to reduce down to 1 and 1, and we end up with iron sulfate like so. And this is a beautiful kind of turquoise colored crystal over here. That's an example of what iron sulfate actually looks like. All right. So what about iron 3? We know that iron can exist in the +2 or +3 oxidation state. And so it's possible that we could also get iron 3 in the product, right? We start with the same reaction on the left, copper sulfate plus iron metal. And this is in the 0 oxidation state. And then when we react those two together, we end up with iron 3 sulfate plus copper, right? So what's happening here? There's a problem with this reaction though, and the fact is it's not balanced, right? If you compare the two irons, right, the iron solid and then the iron and iron sulfate, iron 3 sulfate, there are two irons on the right side, but there's only one iron on the left side. Right, so we have to fix that. If you compare the coppers, they're the same, but if you compare the sulfate anions, there's one sulfate on the left side, but there are 3 on the right side. So we need to balance that out. And so the way we do that is to add in some coefficients, right? So if we put a 2 in front of iron, that gives me 2 irons on the left side and on the right side. Right? You have to balance this out. If I put a 3 in front of copper sulfate, that gives me 3 coppers and 3 sulfate anions. And now the only thing left to do is to balance out the copper that's on the right side. So if I put a 3 there, now the reaction is balanced. All right. And so now we can look at the redox reaction. So here again is the net ionic equation where you have iron solid plus copper 2 plus, and the coefficients that we have up top are going to be the same in the net ionic equation, right? So you see that there are 2 irons in the top reaction. In the net ionic equation, you have 2 irons. There's 3 coppers on the left side, and so you have 3 coppers here in the redox reaction. And then there are 2 irons on the right side of the equation, so it's the same in the redox. And then there's 3 coppers on the right side of the arrow, and it's the same in the redox. So when you look at the redox equation based on those coefficients, right, 2 irons lost 3 electrons each, right, and then 3 coppers gained 2 electrons each. So there was an exchange of 6 electrons, right? And so we can write that in the as the half equation, where you have 2 irons, and then that goes to 2 atoms of iron in the +3 oxidation state, and both of those atoms lost 3 electrons, so we have +6 electrons. And we have 3 coppers in the +2 oxidation state, and that means that you have 3 atoms of copper with a +2 charge, and then so you need 2 electrons for each one of those atoms for that charge to go from +2 to 0. So that +6 electrons gives me copper 0 reduced. All right. All right. So here's that second reaction, and I did my best again to build the molecular structure so you can see what it looks like. And so here you have iron 0 coming in, colliding with copper to knock it out. Right. You lose copper, and then you end up with Fe2SO4 3, right, which is here. Okay, so you had 2 irons that lost 3 electrons each, You had 3 coppers that lost 2 electrons each. All right, so here's the iron 3 sulfate. It's iron 3 plus SO4 minus 2. Right, you crisscross the charges, and you end up with the 2 down here with iron, and then the 3 outside of a parentheses with SO4. And you can see that here in the molecular formula. There are 2 atoms of iron, and then there are 3 SO4 molecules, SO4 polyatomic, which are here, here, and here.